All right. Hey, a little bit of notes here on our boy, I think this is chapter 8, maybe. Holy cow, we're really moving. And when we're mainly gonna be talking about momentum and impulse, are gonna be the two things. A little shorter chapter. I think the challenging math is behind us, and actually this is kind of the last chapter of motion that we have. After this, we're gonna be going through like waves and optics and some of those, the more obscure things in there. So I'll go through kind of some of the basics here with us today. First of all, what is momentum? All right. Momentum, the definition we get back way back from Isaac Newton. And he wrote his three laws in terms of momentum, which he called the quantity of the motion. Okay, think about that. So it's moving. Well, with what quantity is it moving? Okay, that is its momentum. All right. It's represented by the number P. Super convenient for us, I guess. I guess we already have an M for mass. But what's nice is that the momentum is just the mass times the velocity. Okay, so momentum is mass times velocity. It is a direct relationship. The more massive you are, the faster you're going, the more momentum that you have there. The units are these awkward kilogram meters per second in terms of momentum as things are going. But remember, momentum is just going to be mass times velocity, so not too bad. So Gable, with a mass of 65 kilograms, is running at a velocity of 10 meters per second. His momentum, that's an easy one for us, is just 65 times 10, and we get 650 kilogram meters per second on our example there. All right. So like I said, not a lot of notes for that first worksheet because I thought it was pretty straightforward there. The flip side of momentum is impulse. Okay. Impulse, is related to it that we'll go through, but an impulse is the average force acting for a period of time. Okay. So we know that when we apply forces to things, there is a certain window that we're applying a force, whether it's a parallel squat or it's you're pushing a sled. You are not pushing that sled forever, and you're also not pushing that sled for 0 seconds. There is a period of time in which you push it. The person that is able to push the sled with a great force for a short amount of time creates a different impulse than someone that pushes the sled for a long amount of time with no force there. So we represent impulse by I, at least that one's a little more convenient for us. And then I is going to equal F times that delta T. Okay, so it's whatever force we're acting on, time multiplied by the change in time. Okay, so if it took you 2 seconds, it's going to multiply by 2 seconds. If it took you, 0.2 seconds, we're going to multiply by 0.2 seconds there. And the units are Newton seconds. So Katie catches a softball using a force of 250 newtons. If you think about it, every time you catch, you have to apply a force to stop that ball. If the force is exerted for 0.02 seconds, calculate that impulse. All right, that one's very straightforward. Again, we're going to take 250. Let me pull up my calculator here. We are going to take 250 times 0.02, and we get an impulse of 5 Newton seconds in that example there. Okay, this is what I want to get to today is what is the relationship between impulse and momentum, right? We can use the second law to help explain how momentum is changed by a force acting on it. All right, how do we do this? We're going to rewrite force equals mass times acceleration. We should know that formula by now. And we're going to replace it with, we'll replace acceleration with the change in velocity and change in time. You multiply both sides by time, you get impulse is going to equal a mass times the change in velocity. So like I said, the impulse on an object is inversely related to its momentum there. Okay. The left-hand side, that's the impulse, force times the change in time. Unit for impulse is Newton seconds. We know that. The right-hand side is the change in momentum. All right. So this is how we're going to be calculating changes in momentum. And as we apply forces over time, we know that's going to have a direct effect on the momentum of an object. We apply a great force into an object, it's going to change its momentum. So once again, like I was just saying, the impulse on an object is equal to its change in momentum. So that impulse that we just been figuring out, force equals the change in time, that's going to equal whatever that final momentum was, that's P2, minus the initial momentum, that's P1. Okay, a lot of times P1 might be zero. Maybe it's not moving at all. Maybe P2 is zero. Maybe we're bringing it to a stop. Or sometimes there might be an object that's already moving, and we're going to add an impulse to it, and we're going to add momentum to that object. Okay. If the force is not constant, which it usually isn't, impulse is found by using an average of the force or finding the area under the curve. We're not going to be looking at a lot of graphs. We're going to be looking at the average force of things there. Okay, so let's do one here together. Cassie's driving a 2,200 kilogram SUV. It's a heavy SUV. She's traveling at 26 meters per second. We have a mass, we have a velocity. She can stop the vehicle in 21 seconds by gently applying the brakes. What is the average force? All right, I'm actually going to get into editor mode here. Oh, maybe I can't get it. I'm in view only. Shoot. I cannot get into editor mode. Okay, so we're going to set the two sides equal to each other. All right, so 2,200 times 26 is going to give us, well, I can pull a calculator up for you guys, I think. I'll get mine out here. So 2,200 times 26, that car has a momentum of 57,200 kilogram meters per second. And we know that that momentum is going to equal the force times change in time. We know that she's going to slow down over 21 seconds. So we can take that divided by 21 and we get 2,723 newtons is the force that she's applying throughout that whole distance over the brakes. Next question. If she is going to do the exact same thing, but instead of stopping over 21 seconds, stopping over 21 seconds, she's going to stop over 5.5 seconds instead of dividing by 21. Now we're going to divide by 5.5, and we find out that she needs to apply roughly 5 times the amount of force, 4 times the amount of force, in order to stop 4 times faster. That should not be, this should be pretty intuitive that if we want to stop faster, we need to apply more force. We've been driving before. And if you want to stop slow, you just lightly tap on the brakes. If you want to stop quick, you have to really jam the brakes down hard in order to stop the vehicle there. All right, let's stop there. Yeah. We'll be able to, we'll stop there. We'll talk about collisions. We'll talk about collisions next time. All right. Good luck.